So let me start with a few words about Hubert. I started working for my PhD with Hubert and Saclay in 1986, and I got to share an office with Hubert, who was a few years ahead. And actually, he was a seasoned graduate student. He knew all the ropes, and he did really help me out, a bit like a big brother. So I think he's my big brother in physics. Here's an example. So 1987, so one year later, we had already done some work with Hubert, and it was my very first international conference in Armenia. And the organizers asked Hubert and me to talk about our work with Jean-Bernard Hubert. And you can imagine how nervous I was, but Hubert had this very relaxed and kind attitude, kind of brotherly, and gave me tips on how to write talks. You know, he was only 2 years ahead, but to write talks, to write slides, how to speak in public. And I guess I'm still using his tips today, okay? So working with Hubert and Hubert, both of them, was exciting and challenging. So it was a mix, I would say, of competition and friendship, okay? And I think the best image for that is this hike we made in 1988 in Les Ouches. And I can still picture Jean-Bernard Hubert, you know, leading the way with a really good pace, really hard to follow. And Hubert and I, once in a while, we exchange these looks, these glances, and we try to catch our breath and to follow, you know, and keep up. And I think that was a very good image. So then on this picture, of course, you only see the result, and the result was always nice. Okay. All right, I think it's enough for reminiscences, and let's go to physics. So today I want to tell you a story about new things discovered on a very old model. Okay, so of course this turns around the ice systems, which is like the archetypical integrable systems. So two-dimensional ice, you know, 6 vertex models. I'll explain a little bit about this and what's around it. There was a lot of combinatorial developments around square ice. And I'll show you how, in a sort of very simplistic idea, you can actually study the same system on a triangular lattice rather than on a square lattice, and gives rise to not the 6 vertex model, but 20 vertex model, already studied by Backstar and Kelland in the old days. And I'm gonna try to develop the combinatorics around this new model. I mean, this old model, but in a new way of looking at it. And in particular, some combinatorial wonders, which resemble very much what happens with 6 vertex and its associated combinatorics, and in particular, relation with domino tilings. So there's this thing I call the holy Aztec square. I'll show you what it looks like. And what we found with Emmanuel Guitter is a beautiful connection between 20 vertex and these tiling models. And I'll show you the sketch of the proof, which is very simple and relies really on the integrability of the models. And then I'll go over to thermodynamic properties, such as the Arctic phenomenon and limit shapes in the presence of specific boundary conditions. Okay, so here is the summary on the 6 vertex. Okay, typical configuration. On the square grid, we impose domain wall boundary conditions, but arrows enter horizontally and exit vertically. At each vertex, you have arrow conservation, so 2 entering, 2 outgoing. That gives you 6 possibilities and 6 vertex. Okay, so there's essentially three ways of looking at the 6 vertex model. So the original way here, right, in terms of these arrows. Second way in terms of osculating paths. So you just choose a basic orientation of arrows, and every time you agree with it, you draw an edge of a path. So here everybody agrees, and you decide to detach this into 2 paths, going from the top left to the bottom right. Okay, so here are all the 6 possibilities. And then another formulation, it's more used by combinatorialists, is as alternating sign matrices. So you notice that among those vertices, 4 of them are transmitting vertices. That is, if an arrow enters, it exits in the same direction. And 2 are reflecting vertices. And so you associate zeros to the transmitting vertices and plus or minus 1 to the reflecting vertices according to how they reflect. So this gives rise to these 3 ways of looking at the 6-vertex model: arrow configurations, non-intersecting osculating paths, and alternating sign matrices. All right. So an entire world was hiding behind the 6-vertex model. Okay. So, and this world is a world of combinatorics, really. So it starts with the ASMs in bijection, but then, much more surprisingly, there were other objects called TSS-CPP, plane partitions, essentially, with all sorts of symmetries, and descending plane partitions with other types of symmetries, which end up being counted by the same number of configurations. So a very intriguing thing for combinatorialists was to try to find bijections, and they never could. So these 2 objects don't even talk to each other, but also don't talk to the 6-vertex configurations. Okay, so it's a big mystery why all these objects should be enumerated by the same numbers and how to connect them. And there are very subtle connections. Anyway, what I want to do today is to go over to a triangular lattice as opposed to square lattice. Okay, so how are we going to do this? It's very simple. We have now 6 edges adjacent to each vertex. Okay, we're going to again orient the edges, right? Have arrow configurations, and what we want is that at each vertex, the arrows are conserved. So 3 entering, 3 outgoing arrows at each vertex. So among the 6 edges, you will have to choose 3 entering ones. That is 6 choose 3, 20 choices. Okay, so that's why it's called a 20-vertex model. And here are the 20 vertices. Okay, so in pretty much the same way as I showed you with the 6-vertex, you decide on a basic orientation. Let's say everybody goes down and to the right. Okay, and whenever you agree with those orientations, you paint the edges in red, right? And you make them edges of paths, right? So this first vertex, which agrees with everybody, has actually 3 non-intersecting paths, right? Like this. Okay, and you have all possible combinations here. So you have the 20 local configurations of these osculating paths. They're called Schroder paths because they can have 3 directions: horizontal steps, vertical steps, and diagonal steps. Okay. All right. So we're looking at these configurations of paths. What about boundary conditions? So in the 6-vertex, there were these domain wall boundary conditions that all the arrows were entering horizontally and exiting vertically. So if you think a little bit about it on the triangular lattice, there are many possibilities. But we ended up converging to the simplest we could do. So it started with really being too lazy to draw things on a triangular lattice and rather draw them on a square lattice with a diagonal. Okay, but then you can see the underlying square, and so the natural thing to do was to impose domain wall boundaries on a square grid in this triangular lattice. Okay. So again, everybody enters horizontally and diagonally on the edge, on the east, west, and east sides, okay? And everybody exits on the top and bottom. Okay, now that leaves some ambiguity on the corner edges, because are they part of the bottom or are they part of the east, right? So you have 2 possibilities, which we call domain wall boundary condition 1 and 2. But in fact, it's very simple to see that if you rotate the whole thing by half a turn, right, 180 degrees, you're mapping configurations of the 2 models. So they are the same model looked at in a different way. Okay, so I'm just giving you some configurations of paths that correspond to the configurations of arrows I gave on the left. So you can see my paths are all starting on the west side and ending on the south side, and they go basically to the right and down. Okay. All right, so now I change completely my story. Okay, I forget about the 20 vertex for a second, and I introduce you to some other model, which is a model of domino tilings. So tiling with domino, so there's an underlying square lattice, right? Each domino is just made of two adjacent squares, okay? And you're trying to cover your domain with those dominoes. And here's the domain. It's a bizarre domain. It's almost a square, but not quite, because it has defects here, here, and here, okay? So almost a square, drawn on the tilted square lattice by 45 degrees, right? And then you have this even more bizarre hole in the middle in the form of a cross, okay? So that's why I call it holy Aztec square, you know? And then on top of that, as if it were not enough, I impose rotational symmetry by 2 pi over 4, right? Okay, so this is the model I want to study, okay? All right. So how do I study this? Well, there's a fundamental domain under the 2 pi over 4 rotation, so I can concentrate on that domain, okay? See what happens, and what happens is that basically everything that happens on this side should also happen on that side because there's this rotational symmetry, right? So actually, instead of being just a quarter plane fundamental domain, it's really a cone because I have to identify this side with this side. So I'm really wanting to tile a cone. So I represented that cone here. Now, there's a very convenient way of representing a tiling by non-intersecting paths by using this dictionary. So the square lattice is naturally bicolored, black and white in checkerboard, right? So each domino really can take 4 configurations, right? Depending on where the dark square comes, if it's on top or on the bottom, or here on top or on the bottom, right? So you have 4 types of dominoes. And so we decide to paint, again, edges of a path across those dominoes and leave the last domino empty, okay? So we have these 4 dominoes, and now we can replace the data of the tiling by the data of the paths, okay? So now we're looking at a cone with paths winding around it, and those paths are, again, Schroder paths. They have horizontal, vertical, or diagonal steps, right? And they must be non-intersecting. So they are no longer osculating, but non-intersecting. So really, this model is a sort of similar in flavor to the 20 vertex model, except that instead of having interacting fermions via these kissing points, we have non-interacting fermions via this non-intersection condition, okay? So it's like removing a little bit of the interaction of a 20 vertex, okay? Nevertheless, what happens here is that you can count. It's very easy to count. Once you have formulated things in terms of paths, you can use the celebrated Gesell-Vienno theorem, which tells you what the partition function for a set of paths with fixed ends is, right, with certain weights, bottom weights on those paths. And you combine this Gesell-Vienno theorem with the Cauchy-Binet identity for determinant of identity plus a matrix. So very simple, when you do determinant of identity plus a matrix, it's just the sum over all minors, which are diagonal, that is, in which the first entry and second entries form the same set, right? So you erase, if you want, you erase rows and columns with the same indices in the matrix, you keep the rest and you compute the determinant, you sum all this, and that gives you determinant of identity plus n. But now a matrix with entries in 2 sets like this is actually counting for you via the Gesell-Vienno theorem the number, the partition function for paths with positions of the starting points at certain integers, I1, I2 up to Ik, and positions of the ending point at the same positions. So this matrix M is actually counting the paths. So a very simple way of representing this matrix M is via a generating function. If you want, it's a sort of a Fourier transform of a matrix, because it's a priori, it can be an infinite matrix, right? So we are representing it by the infinite generating function with power zi wj for the element mij, right? And so we extract the term of power Zi Wj to get the Mij matrix element. And now we take the determinant over the n first rows and columns of this matrix. Now, why is this matrix given by this very simple fraction? Well, at least I can explain very simply this denominator here, right? So there's Z, W, and ZW. So you can really think of my 4 dominoes, or my 4 possible steps or absence of steps in the path, as carrying a weight W, Z, and ZW. So W would be for going down by 1 step, Z going right, and ZW by going diagonally, right? And so this 1 over 1 minus Z minus W minus ZW is just the generating function for all possible steps in your paths, right? And so now this formula really counts exactly what we want, okay? So a very, very simple and compact formula that we came up with Emmanuel Guitter. All right, so you start crunching numbers, right? So you compute the number of configurations, and let me insist on this 23 here. So 23 would be for size 3, right? So I have this Aztec quasi-square, and I count the number of rotationally invariant domino tilings. I find 23. If you don't believe me, you just count how many there are on these slides. And that's my 23 configurations. And I represented the paths. So you see, there are situations with no path, with 1 path, and with 2 paths, right? All possible tilings are represented here. Now, the miracle here is that if I look at the same size number of configurations of my domain wall boundary condition 20 vertex model, I find the same number, 23. Okay. And so, all right, so conjecture, these are the same numbers, right? If I change the size, and it can actually be proved. So let me show you how to deal with the 20 vertex side now of this identity. So the first thing is that triangular lattice means that these vertices are 6 valent, and this is not so nice. So the first thing is to resolve this singularity into normal intersections between 2 lines. So what you do is you take all these diagonal lines and push them a little bit away, right? So you end up with another lattice, which is called the Kagome lattice. Okay, so Kagome is not because of a Japanese physicist, it's because it's a method of waving baskets. Okay, all right. So here is another lattice of Kagome, which I found in a grocery store in Kyoto. And it will play a crucial role in my talk, so that's why I'm flashing it to you. Okay. Anyway, let's go back to our 20 vertex model. So we want to represent, we still haven't chosen Boltzmann weights for this model. And the idea is that the right way, the nice way of choosing Boltzmann weight for this model is actually to choose Boltzmann weight for the Kagome model by just using the 6 vertex Boltzmann weights at each of these 3. So you see, we have created 3 sublattices now, right? So there's a sublattice where the lines cross at a right angle, right? But there's also vertical diagonal and horizontal diagonal, right? So these are 3 sublattices. And so I can decide to take 3 arbitrary 6 vertex models on each of these 3 sublattices, and out of them build Boltzmann weights for the 20 vertex model, right? By just summing over all possible configurations of these newly created triangles, which I paint in blue here. Okay, so here it is. You have the weights of the number 1, number 2, number 3 sublattice 6 vertex models, right? Now you define the weights for your 20 vertex models as having moved slightly the diagonal line down, let's say, as the sum over all possible configurations of the new inner triangles of the corresponding weights that you get in the 6 vertex models, right? And now you're going to demand integrability, that is, that this resolving the singularity by pushing it the diagonal down, you could have, of course, pushed it up, right? But then that gives you different numbers. So you have all these identities that you have to satisfy, right? And so there's a solution, there's a very nice solution, and you have a 3-parameter family of Boltzmann weights, which I summarize here. So they are grouped just like the 6 vertex was not seeing the difference between orientation, global orientations of arrows. Same thing here, right? So each guy always goes with his complement, okay? But now they are grouped into 7 sets of Boltzmann weights, and here are the Boltzmann weights expressed in terms of quantum parameters and spectral parameters that one usually uses in 6 vertex. Okay, so a nice set of Boltzmann weights making the system integrable. One remark here is that the uniform weights can be attained by special values of all these parameters. So eta equals pi over 8 means that q is a root of -1. Okay, so q to the 8 is -1. Okay, and they correspond actually to the 3 sublattice 6 vertex model weights not being uniform. You see, you are uniform in 20 vertex, but you're not uniform in 6 vertex. So you have the square root of 2 floating around, right? And all these 6 vertex model has the same value of anisotropy, the delta, which is 1 over square root of 2. But the claim here is that somewhere hiding in these 6 vertex models are these non-conventional values of ABC is the combinatorics of the 20 vertex model. Okay, and so let me now show you precisely what happens. So we want to compute the partition function, let's say, of this model, right? So let's transform it, actually. So by transforming, so the first thing I do here is just stretch the lines a bit. So that's allowed, of course, no problem. And now I'm pushing half of the diagonal lines up and the other half down. So I can do that because of my Young-Backstar relation, right? I arrange for my Boltzmann weights to have this property that you can move the diagonals around the intersections. Okay. And now let's zoom in on what happens here. So you remember everybody was entering horizontally, exiting vertically, okay? So horizontally here, I have all the arrows entering, okay? But because of a conservation law of the 6 vertex, all these arrows are actually conserved, right? So this goes like this goes like this, etc. And you see the next step, of course, it propagates. So at the end of the day, it propagates all the way to the inner square grid, which I have here, okay? So basically, this is a product of bunch of numbers, right? Which we can discard, times what's left, the meat that's left in the sandwich, is actually the 6 vertex model on the sublattice 1, okay? So if you want to count the number of configurations of a 20 vertex model, you just have to multiply all those numbers I pointed to, which actually happen to be all 1, okay, times the partition function of 6 vertex on the sublattice 1 with the weights I pointed out to here, okay? So actually, those numbers that I'm after are really given by some other point of a 6 vertex model. And now let me zoom in on my lattice of Kagome. There's 20 fruit and 6 vegetables in this delicious beverage that you can find in Japan. Okay, so you just had to read the label. Okay, Emmanuel Guitter made this remark. I took this picture, sent it to him, and he made this remark by zooming in. All right, so here's the theorem, right? My numbers are counted by the 6 vertex model at these special points. So how do you conclude now? Well, we had an explicit determinant formula for this holy Aztec square domino tiling problem, right? Now we also have an explicit formula, which also takes the form of a determinant, thanks to Izergin and Korepin for the 6 vertex model. We just have to take the right homogeneous limit, right? Compare with the result of this other determinant, and you find that both determinants actually are truncations of infinite matrices with very simple generating functions, rational functions like that. And then just a relation between the rational functions in the 2 cases allows you to show that all the determinants are the same, okay? And as a bonus, you also can find that there are refinements of this correspondence. Okay, so I just gave you a flavor of how one shows the correspondence between these two enumerations, but there's absolutely no idea why this is the case, right? But this is really the triangular version of one of these earlier magical connections that there were between the 6-vertex model, or alternating sign matrices, if you want, and descending plane partitions, which were, again, basically non-intersecting paths on a cone. Okay. So now I want to discuss the last problem, which is in the presence of those domain wall boundary conditions, it is likely that some crystalline phases are going to be created in the corners, and that there will be some freedom in the middle, so much so that you will have an Arctic phenomenon taking place. Okay, so instead of describing it with words, let me just show you large simulations of my 20-vertex model. So if I zoom in on some corners, you can see here the presence of one type of crystalline phase, another type. If I go down to this corner, here is another type of crystalline phase, and here another type, and here another type. So in total, 6 types of crystalline phases are appearing in this picture. But more amusingly, what you see here is as the size becomes larger and larger, and you look at a typical configuration, you start seeing this shape, right? Which is like a coffee bean. So how to determine these shapes, okay? So there's a very, very handy method called the tangent method, which has been introduced by Colomo and Sportiello recently, and which consists in doing this thing. So you have a soup of paths, right, with their ends attached to the left and to the bottom of the picture. So you're going to take the topmost one and pull its end up so that now it will sort of be free when it's away from the other paths, but then interact with the other paths in its final stages, okay? And so you're going to use this path as a sort of snitch that's going to tell you something about what the other paths are doing, right? So it's spying on the other paths. And asymptotically, here is what's happening. The other paths don't care about this extra path, right? So they live their life and they still form their Arctic curve here. Now, this path, once it's sufficiently far away, if I have moved it to a fixed point here, it will follow a straight line. So actually, it will follow a tangent here to the Arctic curve. So the only problem is to find what this point is. This point is the most likely exit point from the domain, right? So you can find it by some saddle point technique. If you compute the partition function here, the partition function there, and you look at what's the dominant contribution to the sum over the position here, you will find the most likely position. And that's the idea. Once you have a most likely position, you have this point that you fixed by hand. This line is tangent to the Arctic curve. So the envelope of a family of lines you find this way is going to be the Arctic curve. So make this work now. So if you do it for the 6 vertex, here's the situation, right? So you take the topmost path, you look at where it exits, right? So here you have a partition function of 6 vertex modified, in which you impose the exit of this path here, and that's easy to get by just taking a different spectral parameter in the last column, let's say. And here, just a single path in a substrate with 6 vertex weights, right? So that's very easy to compute. So you do this computation. Now you can repeat the same computation with 20 vertex. You just have to find out a connection between the 1-point function boundary of this boundary operator here in the 20 vertex and the 1-point function boundary operator in the 6 vertex. So if you do that, you get this partition function. Here you have to modify, of course, this calculation to get this partition function. You do your saddle point, you find this point, you have the Arctic curve. And so we did that for the 20 vertex model with domain wall boundary condition 1 in uniform weights. And we find a beautiful curve, which I hope you can see here in dashed line. Okay, so we have an exact derivation of this Arctic curve, which is made of several pieces. So it's piecewise analytic Okay, it has all these different analytic pieces. And now you can play, of course, with the 7 weights I gave you, right? So there's a very rich phase diagram, in fact, in this 20 vertex model, because you have more parameters. And so you can get all sorts of amusing Arctic curves. Okay, I show you only 2 of them. So these simulations were done by Berard and Debin. Okay, now I told you this connection with Holy Aztec square domino tilings, right? And that we could even get refinements by using spectral parameters. So actually we can apply the same method with these guys, because the 1-point functions are given in terms of 1-point functions of a 20 vertex model. And this is what we find for the uniform weight domino tiling. And the Arctic curve is this, it has, thankfully, the rotational symmetry of the problem. Okay, so that's a good check. And it's actually this this curve of degree 10, this algebraic curve of degree 10. So it didn't hold on one line, so I put 4 pieces. Okay. So let's put them all together on the same picture, because that's really interesting. So remember, we have a 20 vertex problem here, enumerated configurations enumerated by a certain number. We had this Holy Aztec square domino tiling problem with rotational symmetry in this larger square, enumerated by the same number. And now what we find is that one portion of Arctic curve is actually the same in both models. That is, if I take this portion of Arctic curve that I determined for the 20 vertex model and take its analytic continuation, it will be my clover leaf here. Okay, so I think this is one way of seeing that we can go beyond just merely saying these are the same numbers. There's no bijection, but the best thing next to a bijection is to see that they share some asymptotic properties like this Arctic curve. Okay, the next question would be, of course, what are the fluctuations around these Arctic curves? Are they universal? Are they given by KPZ, like everybody is trying to guess? That's another question. And just here, let me conclude by wishing Hubert a very happy 60th birthday and many other birthdays after that. Thank you.
Thanks, Philippe, for this fascinating talk. I give the microphone to Jesper, who has, of course, the first question.
Hi, Philippe, this is Jesper. So,
hello.
Hi, could you show this beverage again?
Ah, yes.
I think you overlooked something.
Aha. There.
So let's see, how many % of something was there again?
Yes, there's a 60 plus 40 equals 100. Yeah,
okay.
Okay, I have no idea. If there's a Japanese person in the audience, maybe they can help us out.
The 60 is for Hubert and the 40 is for me, I guess, more or less. Anyway.
Okay, all right, we can say that.
So anyway, so I just wanted to... So ever since I read this paper by Kelland, wasn't it Kelland?
Yes, Kelland.
Yes, on the 20 vertex model and this follow-up paper by Backstar, I found that it was a bit cheating that they managed to draw apart a triangular or a Kagome lattice like this with those framing boundary conditions. So I was wondering, so can't you, is it possible to introduce some kind of boundary conditions or correlation functions so that you cannot draw your spectral lines around that like that?
Absolutely. So the simplest way of doing this is to alternate arrows. You see, the key here, here. The key here, which allowed you to push these lines through, right, was that these arrows were actually all pointing in the same direction, right? So imagine you have a boundary condition in which the arrows, say, alternate like this, okay? Then, of course, you have a problem because you learn nothing here, right? So you cannot really undo anything. So having pushed the lines away doesn't really help because it tells you nothing about the arrow configurations on the intermediate stages here.
Yes.
So it's only in very specific Domino-like boundary conditions that you're going to be able to say something, right? And indeed, the argument of Backstar, I think it's in his book, no, or was to just push the lines away.
Boundary conditions or something in his book, I think.
Yeah, yeah, and I believe, yeah, there's some kind of cheating there. But here it works really because of this particular choice of boundary conditions. Yeah, I agree.
Backstar cheats a little bit because in his setup there are boundary terms, but he neglects them because he's just going for the bulk free energy or something.
Yeah, and here we can see that the boundary is crucial, right? I mean,
indeed,
certainly the free energy and all that stuff is going to be very different if you change boundary conditions.
So another thing I was wondering about was this when you put it on this cone. So
yes,
it's very nice to put CFTs on a cone because then you get these singularities like in the Cardi-Peschel paper. But unfortunately, I guess you won't get any logarithms or anything for anything here because your central charge must presumably be zero since you can do combinatorics.
Yeah. This is really some free fermion system, you know, like some dimer. It's basically a dimer system. Well.
Oh, maybe so. It's not C equals 0 then it's C equals.
No. It's not C equals 0. No, not at all. It's a dimer problem.
But then, according to Cardi-Peschel, shouldn't you get when you count stuff on a cone? Shouldn't you get some contribution to the free energy that goes like C times log of the size or something?
Good question. Although I know that the free energy in both cases is going to be the same, right? I mean, at least the one in the uniform case is the same, right? Because the numbers are the same, right?
It's possible that your cone is your conical singularity maybe is neutralized by your boundary condition changing operators for those specific boundary conditions.
It's possible. Yes, I'm thinking something like that should happen because I don't see really any possibility for logarithmic corrections here. I might be wrong. Oh, good question, actually. Good question.
Okay, well, we can talk about it more.
Mm-hmm.
Hello, Philippe, it's Hubert here.
Hubert.
Thank you, c'est bon de te voir. I wanted just to make a joke, but with global warming, your interest in Arctic curves is really going to melt away. And
probably. I was just trying to break the ice.
Thank you. All right, that's too good. All right, thank you, Philippe.
Thank you.
Yes, so I have a very naive question about the tangent method, just because. So, does it also apply to cases where you have not only 2 phases but 3, like when you have another frozen phase inside the melted region? Like
okay, not that I know. It's a very good question, right? So we know that there are situations. I think the simplest way is to just take the Aztec diamond tiling, but now impose weights on the dominoes that have a certain periodicity, right? Yes. So not uniform weights, but say you take a 2x2 grid of Boltzmann weights and then you repeat that grid everywhere. And so if you do that, you create a new face inside. So basically the thing, instead of looking like just the Arctic circle, it has this four cusp inner curve, inside of which a different phase starts to occur. And you see, it seems to me, I might be wrong, that the tangent method applies to gases of paths, right? And uses some of those paths to tell you something about the rest of the paths, right? And I don't see any way of describing these interfaces in terms of paths themselves, out of which I could take some out, which would tell me something about them. So it's not done yet. Now, maybe we just need a new idea, and it could be done also. But this is an excellent question. And at the time, I don't know.
Okay, with this excellent question, I think we should close the talk of Philippe and thank him again for his talk.